right, good morning, everyone. We are Jamn Engineering. I'm Allie Knowles.
Nice McGuire.
Jack Hoffman.
Nick Portwine.
Today, we'll be talking to you about our senior design project. Our project is located in Escanaba, Michigan, in the Sioux Hills neighborhood, and we partnered with the Army Corps of Engineers to work on this water management project. Our main point of contact is Garrett Ray, and the project we're trying to help find a solution to is the community is experiencing heavy flooding despite being on a hill, and they experience flooded basements annually and they need a solution. Our specific scope is that we're tasked with the environmental design, specifically with water and groundwater management and dewatering well pump design. As an overview, we'll go over the existing groundwater and aquifer conditions, soil types, permits required, proposed well locations, wetland identification, demolition and removal plans, our flow model, pump selection and design, a construction schedule and cost estimate, and our recommendation moving forward.
So getting into the existing groundwater and aquifer conditions, the well logs in the Sioux Hill neighborhood all consistently report about a 30 to 50 layer of sand below, which terminates at a clay layer. And that is acting as an unconfined aquifer, which means that it is fed by surface water that falls onto the ground as rain or snow melt. And so all that water, because there's no drains or any infrastructure, it all infiltrates into the ground, feeding this aquifer. And so in times of spring and snow melt, that aquifer often floods and it seeps into basements. Right now, the well logs are reporting a static water level below the substrate about 10 to 20 feet below grade. And if we look at one of these well logs, that you can see that this is an example of one that we looked at up there in the right corner. It's the example of kind of the description of the substrate below the surface, sand, and then terminating at clay and hard pan. And this pumping test found that the static water level was 15 feet below grade.
So looking into the soil types in depth, as you can see, our three proposed well locations are the red dots there, and they're all located in a Kalkaska sand region, which this characteristics of this soil type are typically elevation between 570 feet to 1,970 feet. Typically, it's after the organic plant layer, it's all sand, and it typically has a deep water table depth of 80 feet, and the frequency of flooding and ponding is none. However, due to that hard pan layer, that is where they're experiencing their flooding issues. Next, looking into permits needed to complete this project. The first one is the National Pollutant Discharge Elimination System. This is designed for MS4, which is municipal separate storm sewers. These systems are owned by the state, city, town, village, or public entity discharging into U.S. waters, and they're designed and used to collect stormwater, but they are not part of a sewer or drainage system going into a publicly owned treatment work. And this part of the Clean Water Act allows point source discharge into waterways. So we want to make sure the water that we're pumping out is clean and not going to harm the ecosystem upon discharge. Other permits that will be needed to complete this project are the Eagle and Army Corps joint permit. This permit is kind of a blanket permit that covers all state and federal permits regarding water. So wetlands, floodplains, dams, inland lakes, streams, Great Lake bottomlands, critical dunes, environmental areas, and high-risk erosion areas. We have been in contact with Christine Redden from Eagle, but we have not heard back in regards to this project. In addition, Delta County permits will need to be acquired as well, specifically with soil erosion, building permits, property disturbance, and they'll need to communicate with UPCO for utility easements.
So for our proposed well locations, these locations are pictured on our map here as the three red stars. There's a north location, central location, and southern location. These were from the U.S. Army Corps preliminary report. We also utilize a hydraulic conductivity value from the preliminary report of 33 to 125 centimeters per hour. We designed our model for the higher value, but these well locations can be subject to change, and listed below are some addresses that may be affected by the well installation. So for our wetlands as well, this is also pictured on the map on the screen. It's the lighter green areas. And as of right now, it does not appear that there will be any wetland interference, but this also needs to be reevaluated as this map may not be 100% accurate. And the addresses that have potential for wetland interference are listed below. So this is one of our demolition and removal plans. This is for the north well location. This location is fairly clear, as can be seen by the imagery. Basically, it's just going to need some brush and rocks removed, as well as the overburden removal. And for our central well location, this location is more wooded, so it's going to need a lot of tree removal as well as excavation. And then for our southern well location, this location has the potential to be clear. These locations are not like set, they can be changed, a little bit. So it may end up in the trees a little more, or it may end up in the yard in a clear area. So it's all dependent on where it exactly goes.
So the first step in designing this project was to create a transient flow model. And what transient means is that it reflects realistic conditions and how is the aquifer changing in periods of increased infiltration, snow melt, and rain. And so that was the first step in designing this project. We were given a steady state model by the U.S. Army Corps of Engineers, and that would overestimate the amount of water that would be pumped out of the aquifer, because it's assuming that it's completely being recharged at all times. And so the transient model will give us a good indication of how the aquifer will react, and it will help us kind of understand when we can need to operate these pumps, when we can shut them off, and how the aquifer will respond to that. And so the first thing we had to do that was to get precipitation data to calculate recharge. And so we used a Thornway monthly water budget in Excel to calculate the recharge values. And these are the values of precipitation and climate data that were inputted into that calculator. And from that, we were able to calculate recharge values. And the way ModFlow works is it operates with stress periods. And so each one of these is a different stress period. The colors are not showing up very well, but what we did was we averaged the stress period or the recharge values for each month, and we compiled them into one value. And that was the value we used for that month. So we're assuming that the recharge from April to June is that value. As you can see in these summer months, the recharge is negative, which means not a lot of water is infiltrating into the soil, which means that we could probably shut the pumps off. And so these were the values that were input into ModFlow, and these helped us create that transient model.
So getting into some of the issues that we had with the given ModFlow models, they were in steady state, and we were asked to convert them and make a transient model. However, as you'll see in later slides, the boundary that they used was just really too small to give an accurate description of the area. They used a general head boundary as well, which sets the head at the boundary, meaning that nothing is going to affect the system inside or outside. And there's not really any issue with that unless the boundary is too small. So what we went ahead and did was, with the help of Dr. Gerke, we constructed a new model. This is a little illustration with their model. I was doing some weird things. This is the boundary here, and this is the affected area of the homes. And the water is being, this is a drawdown map, so the water is being pulled all from basically exclusively from the south. And if you go to the next slide, we grabbed some pictures from GeoWebface. So these are wellhead protection areas. If we were to draw that same circle of affected area, these wells would be in that affected area. So as you can see, like existing wells in that area are pulling from the north and west regions. So the model showing us that the pumps are pulling from the south really doesn't make a whole lot of sense. So getting into the new model, we established a much larger boundary, the boundary being this bigger circle and still having that affected area. We bounded the top through some natural topography, and then on the other sides, we bounded it by rivers and as well as Lake Michigan here. So another cool thing that Dr. Gerke taught us about was actually calibrating the model. So when we created the boundary, it gave us a calculated surface water level. But we used data from GeoWebFace to input into ModFlow and kind of compare the surface water level to known points from GeoWebFace. So all of these points here are known points. And then through adjusting the hydraulic connectivity and recharge values, we were able to sort of calibrate the model. These bars show how the closeness. So the green represents within 5 meters of the calculated. The yellow represents within 10 meters, and then red is outside of 10 meters, as well as these bars. There's a thick bar in the middle. If the colored bar is below it, then that means it's within that range below, and then as well as above that bar. So after we calibrated the model and found an adequate recharge value and hydraulic connectivity, we inputted all of the data that Jack mentioned for the transient model, and we ran some simulations and found that a pumping rate of 425 gallons per minute for each of the 3 wells would satisfy the groundwater drawdown that we need. Based on this map in the affected region, we're looking at somewhere in the range of like 6 to 10 meters of drawdown, which is more than what we need. We really only need 2 to 4 meters to get it below the basement level. But if we create enough drawdown in the 6 to 10 region, we can shut the pumps off for most of the year. And then this is a cool thing. This is ModPath. So it tracks particles, and this is kind of a way we check to see if the wells were kind of doing what they were supposed to. And as you can see, these 3 wells really match well with the existing wells in that area from the wellhead protection areas.
So for our pump selection and well pump design, we determined that the wells would need to be 30 foot deep or the diameter of 1 foot. Our recommendation is rotary drilling. This is kind of the predominant method used in UP, especially for shallow wells. The well casing will need to be ASTM F480, 10-inch casing, and there will be a 2-inch annular space since the borehole will be a diameter of 1 foot. So this will be filled with gravel. After this is bored, the pump suction can be inserted into the well, and then it will need a filter or screen to protect the pump. So at a diameter of an 8-inch filter with an intake area of 173 square inches per foot of screen, we determined that a filter 8 foot in length will need to be used to allow for an intake of 430 gallons per minute. And this drawing here shows our well pump design detail. We recommended the Johnson High Flow 304 stainless steel well screen is used. And this just shows our well boring and well casing detail on here. So for our construction schedule, we had a couple major tasks, and this is just for well pump design, their well pump installation. So for the pump house install and the pump install and connection, the longest task is 9 days. Well drilling is the next longest task. This is going to take approximately 5 days. And the remaining tasks are all very short, scheduled for 1 day. And this includes mobilization, site clearing and grading, well casing install, and the site cleanup. And then for our cost estimate, our most expensive items were the pump, motor, and well drilling costs. So this leaves us with a total cost of $48,600. And we'd also like to point out we need to factor in an additional $6,500 electricity cost for yearly pump operation.
So our recommendation moving forward, in addition to our scope of the project, there are 2 other groups. One designing the pump house, so to go over the well, and then another to design the sewers to take all the water from the pumps to discharge it into the creek. So with that in mind, both of those projects have an additional cost. So our recommendation is to investigate the drain tile solution. What preliminary design was done by the Army Corps of Engineers, and they determined it to be a little bit too invasive for their scope of the project. But we recommend that they create a ModFlow model to depict the horizontal drainage system for comparison of the effectiveness for each solution, as well as do an in-depth cost analysis for each solution, because the drain tile solution would have a one-time cost and there wouldn't be an annual energy demand need. And the main concern with the drain tile solution is that you'd have to route around all existing utilities.
Robert,
Would be more disruptive, but it would be something to consider.
Hmm?
And then last.
Somebody?
I'm watching a Zoom presentation on the solution for a water problem.
And then, our last solution would be to, investigate cost and feasibility of installing 2 sump pumps per house and see if that would be enough, water discharge for this, solution. And then going into a few challenges we had, obviously we talked about the mod flow design challenge. This was a really big, kind of setback for us because we didn't come to the realization until middle or 2/3 into the semester. So it was a pretty busy week for Max and Jack figuring that out. But another challenge we also came into too is since there were 3 groups working on the same design, just finding like locations that optimized for everyone. Because we picked our well location based on what would be best for our project, but it's not necessarily what's best for doing the pump house design. So it is variable, and you know the pumps could move a few feet here or there, but overall that was a little bit of a challenge that we encountered. And then last, we have a few acknowledgements. First, a big special thank you to Dr. Melanie Watkins, who is our senior design professor this semester. We just want to thank you for all your guidance and advice. And then a huge thank you to Dr. John Gerke, who helped us with the mod flow design. He works here in the geohydrology. He teaches geohydrology. So his expertise with the mod flow design was super valuable to us, and we definitely learned a lot from that. So that finishes up our briefing here. Do we have any questions?
So this isn't mod flow related, this is more on the well design. I've never seen you before, Ali, even though I've had you in class, but only in COVID times. Did you check on the well design that you could actually produce 400 gallons per minute? Because those are pretty shallow wells. Those are only 30 feet deep. And you have to, if you're gonna pump that fast, you're gonna have a lot of drawdown in the well itself.
Yeah, so we were kind of running out of time. And with our given expertise, we probably would have needed some assistance in those calculations. I looked into some pump design, and the pump that we actually chose needs roughly 30 meters of head operate for like the manual, which you can't get in our well. So it's kind of what we used last minute just to satisfy the pumping rate, but definitely needs to be investigated further.
That's a good question. So I was wondering about the head, right when they got finished with it, like where the head came from. So
Yeah, I saw that they were using a suction lift pump, and that got me concerned right away. So that was like, when the choice of 2 alternatives, you pick the worst one. I understand time.
Yeah. And my other question, I was just wondering if you could speak a little bit about the flow rate that Army Corps gave you for the steady state model, and then compare that with the one that you determined from the transient model. And I don't know if you were surprised.
Yes, the first model, they gave us a number that was about like 150 gallons per minute, I think, and ours was 300 gallons per minute more than that initial estimate from the steady state model. That could have been because of the model being incorrect that they designed. It could also be just because of the assumption that the hydraulic conductivity in that entire model we made, we're assuming that's the same. We were forced to make a lot of assumptions because it is a model. Every model is incorrect. It's gonna overestimate or underestimate certain things here and there. But, I mean, 400 gallons per minute is quite a bit, and it seems like that number was a bit shocking. We were expecting it to be lower, like we said, because we thought that a steady state model should overestimate that flow rate, but yeah, it takes a lot of data to create a perfectly accurate model. So further investigation could certainly be done into making that number more correct.
Anybody else have any?
Well, one practical question that would be interesting to discuss is the locations of those wells. Like, how did you come about with those? Did you explore other options, putting, doing 2 wells instead of 3 or 4 instead of 3 or different locations?
Those were per the recommendation of the Corps. Like they had a whole preliminary report that they gave us, and we were basing a lot about that, with their recommendations and working with what we thought was what they were going to go ahead with through the project. So we didn't really understand if we could change a ton of that or if that was set in stone, but we didn't investigate the use of just 1 well or 2 wells or even changing those locations drastically.
Well, nice work on that project.